All right, at the time of the 2016 conference, most of us had already come to grips with workflows and mechanisms to expand our modeling of civil infrastructure into the solid modeling realms of trimesh pavements, plus linear elements such as curbs and barrier systems. We were already getting pretty smart at reading in structural models in from Revit or even generated in 3D and AutoCAD. And 2 years later, the focus on the digital engineering modeling effort has grown even more intense with seemingly endless demands to expand the content and depth of our 3D models. All this extra output is needed to come without penalizing the design effort we put into the generation of our end product. Now, a critical word in that last sentence is the word design, and it goes a long way to explain the major difference between the process that goes into developing a traditional building information model and a modern digital civil engineering model. Even the difference between the terms structural drafter and civil designer gives additional clues to this difference. Virtually all the workflows and driving forces behind generating a structural BIM revolves around progressively bolting on more and more detail as the design evolves, with nearly all the detail embellishments being added to a virtually static framework. In a civil or linear engineering design, as the BIM PowerPoint people like to call our work, there is never really any guarantee that even the most detailed chair object is in the final location, or that the 10 chairs may well become 8, as we optimize our designs to give our clients the most cost-effective, safe and practical design, invariably through a process of intensive iteration that can even continue into detailed design at times. To be frank, a single majestic pass through a civil engineering design, progressively adding more and more detail to the original concept, is probably a good indication you're just wasting your client's money by delivering a detailed but non-optimized solution. A civil engineering design is a dynamic process, and every detail we need to add to our models has to be flexible and self-healing, adapting to the many ongoing design changes brought about by the optimization process to prevent modeling errors. We can never allow ourselves to be painted into a corner, unwilling to make major improvements or updates to our alignments and designs, because it is just too hard to make any manual changes that result. To me, the actual term BIM and phrase building information model in many cases has come to represent the effort to shoehorn a civil engineering model into a system designed around a building or structural framework. And a classic example of this is the mindset that pretends a road is just a really, really tall building with cars driving along it, and that the floors are regularly shaped segments along the road. Of course, roads are notoriously uncooperative and have awkward stuff in it like interchanges, which kind of pushes the long, skinny building analogy a smidgen, and hopefully that impractical concept is out evolved really quickly. Before we go into the main focus of the talk, I'd like to highlight the main purposes of the Federated Linear Engineering Model. And by far the most important is that of space-proofing, eradicating clashes between objects created by the various design teams who contribute to the final design. And this has always been the cause of many last-minute frantic design changes out on site, when most of these clashes were finally discovered. Of course, to run this space-proofing or clash detection process, which is not always a formal reporting process, as it also includes the simple but always effective eyeballs, you need to have all these objects created to the level of detail appropriate to their use in the digital engineering model. This then leads to the debate about what constitutes an appropriate level of detail for a particular object. So if you take up the modeling of a top of an access chamber, for example, does adding the surface textures really add to the value of the space-proofing process? And as you continue to work your way through the list of details that do not contribute to the space-proofing function of this object, you eventually get something that takes up the room of the riser and the lid, and which is located at where the access point will be relative to the pipe configuration, as this may impact on surface features. One of the other important uses of these civil objects are as placeholders of additional information or metadata about the object, which means that unnecessary detail does not need to be crammed into the civil objects, particularly when most of these are actually standard objects. And this additional information can be provided simply by referencing the documents containing this additional detail. An example of unnecessary detail is including something like a physical grate in your model of civil objects. This level of detail is really just a quick way to bloat your model data size, with little real benefit for the primary reasons for modeling these objects in the first place. A solid object taking up the space occupied by the grate, with metadata attached to it, has exactly the same value without the data footprint, and if peering into access holes is important in your life, you can always apply a blend to the solid trimesh to satisfy your very special needs. Humans are primarily visual creatures, if the popularity of drivel like Love Island is anything to go by. And we are programmed to think that the level of pleasing superficial visual detail is directly comparable to its true value in this world. In 12D world, a classic example is something simple like non-textured versus textured tins that you see time and time again in people's projects. It looks pretty and visually appealing, but the true value of the 3D model in a perspective view is shown in a simpler but correspondingly more valuable non-rendered way when design abnormalities are visible and can be identified and rectified. Our 3D models we produce are engineering models. They are not visualization models, and this is particularly the case when trying to inject realism into our models to make them theoretically better actually reduces their true engineering value. There's an ongoing debate about how we model hybrid linear objects such as guardrail, where we can use the realistic-looking 12D model extruders to show the posts and rail for guardrail, and even use these extrudes for sight distance checks. Although you should be aware of the reference point of the 12D library extrude to use this accurately. Our guardrail snippet produces a trimesh region representing the space above ground for sight distance checking and another below ground that the guardrail installation will occupy for clash detection. Our civil designers keep challenging the engineering value of modeling individual posts and repeatedly point out that this can actually be misleading to apply interval-based posts based on the extents of the strings that we designed to represent the guardrail. Even if you excluded end treatments and simply paste out in 2-meter steps from the start of the guardrail string, this process starts to unravel where the guardrail passes from one MTF function to another, which results in a new string and a reset in the post spacing. This means that the posts are potentially in the wrong location, and you could get false positives when running clash detection reports. False negatives that flag further investigation are hugely more acceptable than false positives that can mask potential problems. The potential clashes we get with other civil objects in the zone that the guardrail posts could occupy can be evaluated, and the spacing of the posts flags for adjusting on site if that is a possibility, or if the post detail being amended if the object being spanned falls outside this possibility. Our ultimate guardrail output to the federated model does, however, grudgingly concede that we're never truly going to win this argument. So we export a mix of the below-ground post zone, which can be used for underground clash detection, plus the extruded model so the Love Island fans can say, "Ooh, look, pretty guardrail," when they see it. We do, however, ensure we have an attribute stamped on the pretty bits, pointing out that the locations are strictly eye candy only. There is another disturbing part of our treacherous, superficial, detail-obsessed primate brains that immediately jumps to the conclusion that something that looks more detailed is immediately more accurate. There are examples of fence posts being shown in great detail, but being in purely interval-based locations, they're not truly representative of where they'll actually be built. Or in BIM PowerPoint world, the superbly detailed chair is actually in the wrong place. Treating fences and noise walls with the same logic as for guardrail, we run a custom extrude along a superstring represent the fence location, generating a model of the zone where the fence post may be and address the potential clashes more closely when they are identified. Our current challenge in how we model isolated civil objects in a practical manner is doing this in a fashion that does not involve a doctorate in macro programming, so is not limited to a very select few, plus is also completely immune to what we know will be endless design changes as the engineering model is optimized and amended throughout its design lifecycle. Civil objects we need to include in our digital engineering model originate either inside or outside 12D. Inside 12D, we have 3D features such as electrical objects and survey models. Outside 12D, we often have 2D features generated by specialists in other packages such as AutoCAD, with examples like signs and line marking or street lighting and traffic signal layouts. It can be pretty alarming that objects that appear pretty insignificant on a 2D drawing actually occupies an alarming amount of space that we are trying to thread proposed utilities through. The base process we use to get these objects is a very simple one and is something that any one of us can actually do, which we feel is a vital part to any sustainable workflow. When you write out an AutoCAD drawing, a symbol in 12D becomes a block in AutoCAD. If that block is already defined in AutoCAD drawing template using the export process, then the symbol content from 12D is replaced by the block content in AutoCAD. This means that a symbol of a square in 12D can actually become a circle in the resulting AutoCAD drawing. And if it can be a circle, it can be more than that, because it's not limited to 2 dimensions and it's not limited to lines and polylines. And it can obviously contain any level of detail. So a simple square symbol exported from 12D is now a detailed 3D object in the drawing. Plus it is using the Z value of the 12D object. If you read that drawing back into 12D, exploding the AutoCAD block in the process, you now have a trimesh of the civil object in 12D. The system needed to support this process is also simple, with a library of simple holding symbols. And even the definition of a single circle in the symbols.4D file is sufficient and has a very tiny footprint. Because when a project is open, all your symbols that have been defined are automatically loaded into memory. Each civil object or variation of an object has a matching holding symbol. So the data economy of keeping these symbols as simple as possible is important as our library continues to grow exponentially to meet the information demands of the modern digital civil engineering design. The physical 3D object data is actually stored in the AutoCAD template and actually only makes its way into 12D. It's actually physically used. A static utility object such as this light post typically has 3 different definitions relating to its fate in life. It's either a proposed object or an existing object to be retained or removed. And a typical workflow would be to take all the light posts from the survey model, initially assume they are all retained by default, and a renamed copy of the light post sent to a utilities model. Then run a chain that runs a map file to assign the matching holding symbol, route the models out to a 3D DWG, where the template converts the symbols to a light post solid objects and reads it back into 12D, into a trimesh model. To change the state of the existing light posts to be removed, rename those point strings, then run the same chain again, and the trimesh objects update accordingly. I think I'm out of sync, yeah. For most utilities model, this process of identifying those to be removed is a manual one anyway that evolves to match the changes in the civil design. The source of information for proposed utilities or even for dial before you dig layouts is usually from 2D AutoCAD drawing that's read into 12D. The vertices are these points draped onto your supertin surface to assign either design or existing levels to the points and then mapped to solid objects using exactly the same process. The same map file that applies the holding symbol also passes a standard set of attributes, which are then passed to the target block in the drawing template. Unfortunately, while these vertex attributes export to DWG as block attributes, they are actually not applied when they're actually read back into 12D, which would make for an important enhancement to this process, passing the block attributes to the trimesh string attributes. Our common data environment for our federated engineering model is inside Navisworks, where we also send data from other sources such as Revit, and formal clash detection reports and other BIM stuff is done by another team to free up our 12D designers to do design stuff. And our most common format of export from 12D is IFC, particularly for objects such as pavements, barrier systems, etc. But there is an annoying deficiency in Navisworks that makes this process frustrating and inefficient. The color of objects written to IFC is captured in IFC as standard RGB ratio values. And read into an IFC viewer like Celebri, you can see the colors successfully being used. The same file read into Navisworks has no color applied. And searching online shows that Autodesk does not use the color of the object, but apparently if enough people think that the color of their object is actually important, they will think about it. Apparently there's a lot of thought involved in actioning this no doubt complex enhancement. And of course what Autodesk wants you to use is Autodesk materials instead of colors, conveniently keeping this entire process in their own suite of software, which may explain why they're dragging their feet with this. To get around this Navisworks issue, our actual process in the chain writes out the holding symbols twice using 2 different DWTs. One where the civil object block is defined as the 3D polymesh faces and colors to be read back into 12D, and the other as the block as Autodesk solids and materials to read into Navisworks. There are a lot more faces and bits to 3D polymesh faces than there are as AutoCAD solids, So as a side benefit, it reduces the volume of information going to the federated model, because not all software can thumb their nose at large data sets like 12D model can. The 12D attributes from the holding symbols are, however, passed on to Navisworks via the DWG block attributes, which is what we need to happen to trimeshes that are read back into 12D. This civil object workflow is obviously not limited to existing and proposed utilities and can be used for other civil objects, such as this bloody great big chunk of concrete that may be needed in anchoring some wire rope safety barrier systems. And remembering the reasons that we are creating these civil objects in the first place is primarily for space proofing. So allowance needs to be made for this hidden piece of concrete the size of a bogan's hot tub. What makes this object different from the light post shown earlier is firstly that the holding symbol needs to be applied to the end of the model wire rope safety barrier string. And secondly, the orientation of the symbol needs to match that of the string terminal. This is currently not a standard feature in 12D. So we've had to resort to a custom macro to place this symbol. Now we have very little to no macro writing skills in-house, but we fortunately know of a macro gun for hire will do almost anything for money. And he wrote us a simple sounding macro to place these symbols for a very modest fee. Our wire rope safety barrier snippet produces a result very similar to the guardrail snippet, plus adds terminal information attribute to the actual marker string, which is then used to place the holding symbol. And when the civil object chain is run, the trimesh terminal objects take up space in the federated model for the BIM folk to play with. Now, Sam's macro is also used to place civil object holding symbols for other directional objects, such as light poles and traffic signals with mast arms. And in theory, if your focus is purely on space proofing and clash detection, it is primarily just the post and footing that's important, and all the other pretty bits, again, are for the Love Island fans. We do, however, want to make viewing the federated model an intuitive experience to allow for easy visual identification of civil objects. And fortunately, setting the orientation to these objects takes very little effort and can actually be automated. So in Queensland Main Road surveys, the mast arms for traffic signals and light poles are represented by 2 points running from the lantern to the base of the pole. And by placing a holding symbol at the end of the string and running the magic civil object chain, you get lights that are correctly orientated with a process that has about the same amount of effort as applying a standard mapping file. Now, I originally thought we were going to need this drawing template-based civil object chain to run on the drainage PPF plans to evolve our drainage network into what is needed for our federated engineering models, but have started investigating the option of drainage trimeshes that are set in the drainage.4d file. And like with the other civil objects shown, it relies on a 3D library of drainage structures to cap off the top of the drainage model chambers, with up to 24 variations needed. Sorry? Poor day when PowerPoint crashes, isn't it? Yeah, but no mention of IBM in this talk, right? So,
I agree.
where? Try again. Right, we talk about the 3D library of drainage structures, with 24 variations needed for each pit style to take into account lintel size, channel width, inflow configuration, and orientation relative to the curb. Now, these have always been defined for hydraulic reasons, but we're now also needed to take into account the curb type, not for hydraulic reasons, but to include in the curb transitions in the trimesh and ultimately the federated model. The top structure of the gully pits and access chambers orientate themselves in the same way as the drainage plan PPF plots, including automatically adapting to the flow direction, so no real additional effort is required from the drainage designers who have better things to do, because the drainage trimeshes update with the standard set pit details process. And I must confess, I had to go take a quiet lie down when I realized that the drainage trimesh also tilts itself to suit the road grade calculated on the set out string, so the final 3D orientation is actually pretty close to the real thing. What is needed though is the cover offset to be preset in the drainage.4d file for each structure type, which automatically trims the top of the chamber to the underside of the trimesh. Now, I haven't worn a drainage designer's anorak for more than a decade now, but I've been told that the setting does not impact on the hydraulic calculations. The truncation, however, does look a little strange in the profile view in drawings, but by converting the drainage model to trimeshes in a chain and adding them to your plot corridor models, you get a better looking result, especially if you plot the drainage network to a no plot color, so you only get the trimeshes shown. Now, this trimesh drainage network is needed for the federated engineering model anyhow, because it's currently the only way to get the drainage trimeshes as solid objects that can then be used as in the clash detection process. Our drainage designers have always modeled the existing drainage network primarily for hydraulic reasons, but it's now used to be included in the federated model. And not one of the processes we have typically had to do pre-BIM is to separate the drainage model into the kind of categories or states that are referred to with the modeling of utilities. One of the reasons is so that the various states can be visually identified or even manipulated visually in the federated engineering model. The engineers and BIM folk get twitchy and alarmed when they see a drainage structure in the middle of the road, even if it is one that's flagged for removal, and there are times when you may need to temporarily hide objects like this. You can currently do this a little awkwardly by incorporating and identifying the pit and pipe names and filtering for these in the drainage trimesh model to split these into submodels. What would be a vast improvement, though, is the ability to access custom attributes of pits and pipes through the network editor, preferably including a pick list to standardize the attributes actually used. This is far more stable than relying on manual pit and pipe names that can all be cleared with a mouse click if you do not have the right box tick. And since I'm pushing my luck, the list of drainage structures in the pit type pull-down list is getting pretty unwieldy, and assuming that this future use group that has been teasing us since version 11 is meant to be for something like the other form of naming groups in 12D, then it would be fantastic to get this technology applied to pit and pipe names, which would make it far easier to navigate and use. Now, the final plan integration of these model drainage structures into our models is adapting the road designs to leave gully pit-shaped holes in our design surfaces and other trimeshes. I'll try to be sneaky by including a boundary string in the drainage pit trimesh definition that could then potentially be used with the V14 trimesh cookie cutter, but unfortunately 12D is too smart for that and was ignored that when reading it into the drainage trimeshes. We can, however, adjust our road strings to suit a drainage object with a bunch of fiddly MTF modifiers, tucking these away inside snippets to avoid alarming those with a delicate constitution. And you can even create a null string containing the tin boundary attribute to automatically cut a hole in any tin that the boundary is actually included in. What's really needed, though, is a new smart modifier chainage that anchors the application of the snippet to the nearest node in the drainage network, so that then when the drainage designers attempt to get their revenge back on us road designers by moving their pits around all the time, the application of the snippet would automatically adjust to heal the road designers. Thank you.